Hola, hi, this is Al, your statistics instructor. Let's get to work. In this video, we are going to do an example where we analyze data coming from a Poisson likelihood, okay, from a Poisson distribution or data with a Poisson likelihood, okay? And something else, we're going to be using a conjugate prior. Let's begin. So that's the problem we would like to tackle. That's the example we would like to talk about. This problem has to do with gunshot residue particles. Okay? Basically, what we want to do here is estimating the average number of GSR particles that may be detected on samples. Okay? So the assumption is that those GSR particle counts have a Poisson distribution with some mean mu. Okay? Okay. So let's try and tackle this problem. First, let me make this bigger here. So let me use an uppercase because it's the random variable we're referring to. So let uppercase y represent the number of gunshot particles. Okay. So what we know about y is that this guy has a Poisson distribution with parameter mu. Okay, now as you can imagine, we are going to be doing this using a Bayesian approach. And we know that in order to do that, we need two main ingredients: the prior distribution and the likelihood function. Okay, so as I said at the beginning of this video, we are going to be using the conjugate prior for a Poisson likelihood. We're going to be using a gamma prior. So let's talk about that gamma prior. We're going to be using a gamma, the conjugate prior, and remember, when we say that we're using the conjugate prior, what we mean is that the prior distribution and the posterior distribution will belong to the same family. Okay? And that's why we like these conjugate families, because then calculations are easy. Okay? So now let me say something about that prior that we're going to be using. Okay, so imagine, right, that these scientists, based on similar past cases, they think that prior mean of 6.5 and a prior standard deviation of 3 makes sense. Okay, so let me just say that based on similar past cases, let me use M to refer to the prior mean 6.5, and let me use S to refer to the prior standard deviation 3. And if the prior standard deviation is 3, that implies that the prior variance, which is the square of the standard deviation, is just 9. Okay? So again, this is based on prior experience from these scientists, these forensic scientists. Okay? So now what we have to do is translate those two numbers, the prior mean and the prior standard deviation, into values for R and V, right? Okay, so let's find R and V. Okay, let's find R and V. So you know that we talked about it, and we actually showed that the expected value of a gamma random variable with parameters R and V is R divided by V, right? So in this case we would have 6.5 equals R divided by V. That would be our first equation that is going to help us define our conjugate prior, the parameters of our conjugate prior, and we know that the variance of a gamma is given by R divided by V squared. Okay? Okay, so now we have to solve that system of equations for R and V, and then we are going to have the member of the gamma distribution family that is going to be reflecting that prior information about our parameter of interest. Okay? Okay. So one way of going about this is just let's solve for R. That would mean that R equals 6.5 times V, right? We do the same for this guy here. For the second equation, R equals 9 times V squared. And then we just use the fact that these two equations have to be satisfied, right? So then what we have is that 6.5 times V equals 9 times V squared, right? So that's equivalent to 9 times oh well, just what we could do is let's divide by V, right? And we're done, right? We divide by V on both sides, right? And then what we have is just that 6.5 divided by 9 equals V. Make sense? Now when we do this, right, if you think about it, when you divide by V, you're assuming that V is different from 0, right? And the thing is that v equals 0 would be also a solution for that equation. But the thing is, if you remember the restrictions for the parameters of a gamma, right? Both r and v have to be greater than 0 in order to have a legit gamma distribution. Okay? So when you do this, just let's be very specific that what we're saying when we do this is because we're assuming that v is greater than 0. Okay? Okay. So let me just here re-express that v in a different way. Let me use fractions. 6.5 is the same as 13 divided by 2. So that would be the numerator. Let me do the denominator. 9 divided by, well, 18 divided by 2 would be the same as 9. Agreed? So in the end, v, if I want to write that guy down as a fraction, is just 13 divided by 18. Make sense? Okay? Okay. So now we have v, right? And then we can easily find r, right? From, say for instance, from this one here, right? From 1, r equals 6.5 times v, right? So from 1, what we have is r equals 6.5 times v. Just plug in what we said is 6.5 is the same as 13 divided by 2. And v happens to be that guy, 13 divided by 18. And then 13 times 13 is 169, right? So 169 divided by 36. Okay? Okay. So, we're done. We have both r and v, right? So let's just say that, okay? That this prior mean and that prior standard deviation that comes from the experience, from past experience of these forensic scientists, well, that is equivalent to a gamma with those parameters, okay? So therefore our prior distribution is a gamma with parameters r 169 divided by 36 and v 13 divided by 18. So we have our first ingredient, okay, our gamma distribution, our gamma prior. Let's talk about the likelihood, okay? Let me open a new one here. So now let's talk about our likelihood. So we know that in order to update our knowledge about the parameter of interest in Bayesian statistics, in order to incorporate data coming from experience, empirical evidence, we use that function, the likelihood. Okay, so now imagine that in this particular case, right, data from an experiment gives you a total particle count, and let me use this y1 plus y2 up to y6. So this experiment was carried out 6 times, right? And it gave you a total particle count of 26. Another way of writing that down would be this, right? You have I going from 1 up to 6 of your yi's. Okay. Okay, so bottom line, you carried out six experiments, right? And you count the total number of particles, right? And that's what you have. Okay, the total number of particles, 26. So the thing is, how do you use that information, right? How do you incorporate it? So in this case, what we have to do is, because we don't have the individual observations, so let me remind you that we talked about, remember, we talked about the MGF, the moment generating function for a Poisson, and also the moment generating function for a sum of Poisson random variables, right? So that result will be useful here. Okay, so I think it was result number 3. So by result 3, right, let me call this guy T, as in the total. T has a Poisson distribution, and since we have 6 of these guys, right, the parameter for T is going to be given by 6 times mu, where mu would be the expected value or the parameter for a single observation, right? Remember that we talked about that result using MGFs. Okay, and that's why we talked about it. So now let me write down the likelihood. The likelihood would be the probability of the random variable t being a particular value, lowercase t, given the parameter mu. Okay, we know that it's going to be a Poisson, and the probability mass function for a Poisson is 6 times mu. In this case, that's the parameter, to the power t, then divided by t factorial, right, e to the power minus 6 mu. Make sense? There we are. So note that we could rewrite this as follows. Okay, this is the same as 6 to the power of t and mu to the t, right? Okay. So what I want you to see here is 6 to the power t is just a constant. T factorial is also a constant. So the likelihood is proportional to, right, if we ignore those constants, to mu to the power of t e to the negative 6 times mu. Make sense? Okay. So we have our likelihood. We also have our prior. Okay, so now we're ready to find our posterior. Okay, let me remind you how we do that. So posterior. So we know that in general it's just, given by a conditional probability, the probability of observing a particular value for our parameter given our data. In this case, we have data about a sum, right? A sum of 6 individual observations, and we used the letter uppercase t to refer to that random variable, and this lowercase t represents a particular value assumed by that random variable. Make sense? Okay, anyway, so in words, we know that the posterior, right, is proportional to your prior times your likelihood, or your likelihood times your prior, it doesn't matter, right? Okay? Okay, so now our likelihood, right, is the probability of observing a particular value of t, total particle count, given mu times, right, our prior p of mu. Okay, where are we? There we are. Okay. So we're using a conjugate. Prior, right? So we are using a gamma prior. Okay. So let me remind you what the prior looks like. But first, let's copy, right, our likelihood. Okay, I think it's this one, the one we want. So likelihood, there we are. But this is a constant, we don't care about this guy. That 1 over t factorial, that's also a constant, and we're using that proportionality symbol, right? So we don't have to worry about those guys. So we have that times our prior, and our prior is gamma, right? So that gamma looks like this, right? So it's v to the power r divided by the gamma function evaluated at r times mu to the power r minus 1 times e to the negative v times mu, right? But These guys are constants, right? So let me get rid of them. That's why I'm using that proportionality sign, that proportionality symbol. Okay? So once we do that, we just realize, let's combine these exponents. So what we end up having is mu to the power t plus r, right? E to the power, to the power minus, and then what we're going to have here is 6 plus v, right, times mu. Make sense? Yeah? And here we also have a minus 1, right? I was forgetting that one there, right? Okay. So when you see something like this, you go, oh, that kernel, meaning that functional form, ignoring the constant, that looks like, you know, the kernel of gamma. So your posterior distribution has a gamma with parameters r star. The new r is the old r plus t. Makes sense? Or t plus r is the same. And then the new v star, is the old v plus 6, right? Note that in this case 6 happens to be the number of observations in your sample, right? So if you think about it, when we talked about this, right, for a sample of size n, the updating rules that we ended up with match with what we have in this example, when in this case we only have the information about the sum of the yi's, the total count. Okay, we don't have the values for each of those individual 6 observations, right? Anyway, so let's go back to where we defined our prior, right? So our prior, right, was this. Let me copy those values here, right? And just say in this case, what we have is that our posterior distribution has an r star t, right, is going to be given by the sum. Remember that that sum was 26, right? So that's what we're going to have there. So it's going to be 26 plus r. R happens to be this guy. Remember, we used that prior mean and prior standard deviation from the past experience of scientists, and then we translated that information into values for our gamma prior, right? V is this guy. So now, for instance, if we want to do inference, say that you wanted or you needed to provide a point estimator, a point estimate for you know, the number of GSR particles, right? A point estimate would be given by the posterior mean, right? Point estimate, one option, posterior mean. And we know that in this case the posterior mean would be just R star divided by V star. And we could find it, right? We will find it. Okay, so let's do the math here. Okay, let's find that. Let's find R star. That happens to be 26 plus 169 divided by 36. So roughly this. And V star, let's find it as well. So 6 plus 13 divided by 18, this. Okay. Okay, so one option would be that 30.69 roughly divided by 6.72 roughly. That would be our point estimate for mu, right? So this we divide it by this. So roughly 4.56. That would be a point estimate for the parameter mu. Okay? But we know that we can do something to supplement that point estimate. For instance, we could provide a credible set, a 95% credible set. Okay? Finding quantiles from our posterior distribution. So let's do that, and let's make a graph of our posterior distribution using R. Okay. So how about, yeah, let me call this guy R star. Let me call this guy here V star. So first, something that I want you to keep in mind is that when you graph a gamma distribution, a gamma random variable in R, you can provide parameters for the shape and the rate, which is the way that you're expressing the probability density function for a gamma, like in your textbook. But there's another way of expressing the probability density function of a gamma random variable using two parameters that we call alpha and beta, right? And in that case, instead of having the shape and the rate, you have the shape and the scale. Okay? So anyway, the one that you want to do here is, and I'm going to remind you that the one that you want is shape, is R. Okay? And rate is V. Okay, so now let me use uppercase M for mean, right? Because we are interested in saying something about mu, right? We're going to create a sequence from 0 to 15. How about a distance of 0.001 between each of those members of the sequence we are creating? Okay, that should work. Now, let me show you something here. We are going to be using the function d gamma, which is going to help you evaluate the probability density of a gamma random variable. Okay, so anyway, can you see that you could define that gamma using the parameter rate or the parameter scale and the parameter shape? Okay, so anyway, the one that you want to be consistent with the way the authors of our textbook are doing things is you want to talk about shape and rate. Okay, so well, so we're going to be using that function. So all we need is we're going to need this guy, right? These points where we're going to evaluate the gamma probability density function, and those two parameters, shape and rate in our case. Okay, so here we go. Our posterior is going to be given by the gamma. We're going to evaluate M. Shape will be R, in this case R star, right? And the one that we want here is rate, and that's going to be V star. Okay. Okay. So now we're going to use that command plot. We know that the syntax is first you need the numbers that go on the horizontal, so we're evaluating here. On the vertical, what we want is these guys, you know, the values of the probability density function evaluated here. And then let's just make it look nice. How about blue, right? That's for color. And then for the label for the x-axis, how about a mu? So let's use expression brackets mu. Okay, and you should be seeing something like this. Okay, so that's our posterior, and that's a graph of our posterior distribution. Now, what we could do is we have a graphical representation of the posterior distribution. We said that, for instance, 4.56 would be a point estimate for mu, right? And how about finding a posterior credible set? So posterior credible set. Using the Q gamma function, right, we're going to find two quantiles. Let's find a 95% credible set. Okay, so we need these two quantiles, right? If you see the difference between these two guys, the probability between these two guys is going to be 95%. So again, what we want is shape to be R star, and we want to use rate, which is V star. Okay, so this is a 95% probability interval. Probability, okay, that's one of the things, that's one of the nice things about using a Bayesian approach. You get to use that word in this case. That's a 95% probability interval or credible set for mu. So between 3.09 and 6.31. Okay? Make sense? Okay, so let's quickly summarize what we did here together, right? So what we did is we analyzed that sort of data, right, using a Bayesian approach. That data set had a binomial likelihood. The data was mathematically modeled using a Poisson distribution. Okay, and to analyze it from a Bayesian perspective, we need not only the likelihood but also a prior distribution. We decided to use a prior from the gamma distribution family because then calculations are easy. We know that gamma distribution family is the conjugate family for data with a Poisson likelihood, meaning that both the prior and the posterior will be gamma. Okay, so we can use those updating rules, right, that we have talked about, right? We derived those rules, right, where R is going to be just the R from the prior, right, plus the sum of your observations, right? And for V star is going to be the old V plus the number of observations. Let me just find that where we had that well, those updating rules. There we are, right? R star is the sum of your yi's of your observations plus the old R, and V star the new parameter for the posterior number of observations plus your old V. These are called the updating rules, and we derive them in general. But something else that we saw here in this example is that if you have the sum, right, you don't need the information from the individual observations, right? As long as you have the sum and the number of observations for that sum, then you can apply this. And we know that the sum of Poisson random variables has a Poisson distribution as well. Okay, so we end up with posterior, that is gamma, and then we can provide, for instance, a point estimate using the posterior mean, or we could do something different, like providing a credible set, right, as far as numerical summaries go, and a graphical representation of our posterior distribution. Make sense? Okay, well, that's it for now. Thank you so much for watching. Please take care and keep working hard. See you next time. Bye.